Hi, welcome to the fourth part of the Android Wavetable Synthesizer app tutorial. In this tutorial series, we want to design and implement a synthesizer app on Android using all the modern technologies and best practices. We have already implemented the view, so the user interface, and the view model, which handles the events triggered by the user. Now, we need to implement the model, so the core of our application. However, since we are writing our audio processing code in C++, we need a way to call the C++ code from Kotlin. In this video, I will show you how to set up a C++ module on Android using CMake, integrate it into the Gradle script, and how to interface with C++ from Kotlin using Java native interface and Kotlin's external functions. First, let's ask ourselves, why do we need to call C++ code for audio processing? You may be wondering why we cannot simply do the audio processing in Kotlin or Java. We could if our processing was very basic. However, audio processing is most efficient if integrated directly with the audio driver. Furthermore, audio processing runs most efficiently if compiled directly to the machine code. These both properties exclude Java or Kotlin from the group of considered languages. Why not use other languages for this purpose? I believe it may be soon possible with Rust, but currently C++ is prevailing in audio programming, including Android. That is also thanks to the Oboe library, which allows us to easily connect to Android's audio driver. We will introduce the Oboe library in the next part of the tutorial. C++ is one of the most important pieces for audio programming at the time of recording this video. If you are interested which part of the C++ language you need to learn for audio programming, check it out in my free audio plugin developer checklist. You can get it for free at WolfSound.com/checklist. And now, let's think, how can we call C++ code from Kotlin? Thanks to the Java-Kotlin interoperability, it is quite easy to call C or C++ functions from Kotlin. For this, we need two parts: external functions in Kotlin and Java native interface JNI bridge. External functions in Kotlin are functions which are declared in Kotlin modules and can be called in Kotlin, but which are defined in C or C++ code. This concept is similar to header file implementation file separation in C and C++. Java Native Interface is a programming framework that allows a programmer to call C, C++ functions from Java and Java methods from C, C++. In this tutorial, you will learn how to call C, C++ functions from Kotlin using these two components. To call C++ code from Kotlin, you need to define the desired functions in Kotlin module as external functions, create a source C++ file, write the definitions of the previously declared functions in C++ using appropriate function signatures defined by the JNI, create a build script for the C++ file. This is typically a CMakeLists.txt file with a shared library target, and adjust the build.gradle script file and load the shared C++ library statically in Kotlin. As this seems quite complex, the best thing we can do is to jump right into Android Studio and go through this process step by step. Alright, we'll start by implementing the Kotlin side of things. So first, let's have a look again on the interface of our Wavetable Synthesizer, which is here. We already implemented it as a login Wavetable Synthesizer, and now we will implement the native Wavetable Synthesizer. So here we go, new Kotlin class file, and we'll call it native Wavetable Synthesizer, because it will call native functions. All right, so let's have it implement the exactly Wavetable Synthesizer interface. implement members. Okay, perfect. And we also need another thing for this, because we now need to be aware whether to create or destroy the native synthesizer handle. So for this, we need to observe the life cycle of our app. So we will make the native wavetable synthesizer react to events of the app going into the background or going back into the foreground. Okay, and as you can see, it doesn't work, and it doesn't work because we need to have another dependency here. And for this, we need to go to our app's build.gradle file, and in the dependencies, we'll specify implementation Android X lifecycle view model compose 2.5.0. And let's see, we need to sync our Gradle files. And now we should be able to import this class exactly. And what we want to have here is we want to implement just on resume and on pause. We'll get to it in a second. So first, let's declare our handle to the native C++ WavetableSynthesizer class. And this will be simply a long, which will hold the memory address. The next thing that we'll need is that we'll need some form of mutual exclusion. So we want to make the access, just the access to our native wavetable synthesizer thread safe, because the UI events, they may happen in different order, in different configuration. And for this, we want to simply make sure that we don't use our synthesizer when it is being destroyed, for example, because then we can corrupt the memory. So we'll have simple synthesizer mutex. And now is the interesting part. So now we define our external functions. These are functions that are declared in Kotlin, but will be defined in the C++ code. So first we'll have a function for creating our synthesizer, right? And then we also need to delete it. And to delete it, we need to pass in the synthesizer handle. So this is an explicit way of writing object-oriented code when the first parameter to a function is always the handle to the object that we're handling. In this case, it's an address. And now what we'll do is we'll define all these functions that are called by the view model, but we declare them with a definition in the C++ file. So we'll have play, and this will also take the synthesizer handle. Then we will have stop. Then we'll also have is playing. And this will of course return a boolean. Then we'll have set frequency. Then we'll have set volume. And then we'll have set wavetable. So a couple of interesting things here. After the handle to our object, we can pass in any remaining parameters, right? And also, as we remember, the wavetable was, I think it's here, it was an enum, right? But this enum is not compatible with a plain C, so we need to pass in an int instead and redefine our enum in the C++ code with the same indices, which is of course not handy, and the best way would be to generate the definitions of these enums from some language independent definition file, but for the sake of this tutorial, this is enough. Okay, and now what we need to do is we need to load our native library. So our native library is a shared library, but we need to load it statically. And this is called like this. So we have a companion object, which may be thought of as containing the static members of a class. And in the init block, we can do the static initialization of this class. And for this, we'll need system and load library and the name of our library, which is WavetableSynthesizer. And this is simply because the WavetableSynthesizer will be a shared library file, and this line ensures that it will be loaded so that when we call these functions, they actually have a definition somewhere and we're not lost in Java virtual machine. Okay, so now let's have a short detour and write the methods of this default lifecycle observer. So what we have here is on resume, and of course the first line that we call is the method from the superclass. And now we'll have a synchronized block, which means that access to it will be protected by the mutex. And here we have synthesizer mutex, exactly. And here we'll create our native handle. And for this, we need a method which is called create native handle if not exists. And this will basically ensure that if the synthesizer handle is different from 0, it will be not created, but if it's equal to 0, then it will be created. And on resume will be called when our app goes into foreground, even on launch, when our activity goes into foreground. And analogously, we'll have on pause. And here again, we need to have this access synchronize, synthesizer mutex, and we'll have, we'll check if the synthesizer exists. So if it's 0, then it means that it does not exist. So we don't want to destroy it twice. So we return simply from this function. But if it does exist, then we call delete. So this is the external function that we defined previously here. And now we set the synthesizer handle to 0, which tells us that actually there's no synthesizer and we need to create it again if we want to use it. And now we'll need this method create native handle if not exists, and it will be private. And what we do here is then if the synthesizer handle is exists, right? So the address is non-zero, then we return. But if it doesn't exist, we call create and assign the value returned by create to the synthesizer handle. And again, you can see that it's an external function. And as you can see, this create native handle if not exists is not synchronized. So we always need to call it inside of a synchronized block. Okay, and now it's a time to implement the remaining part of our methods. And what we'll do here is each of these methods will look basically the same. So we want to, first of all, move the execution to a different thread, not to put the load on the UI thread, So I'll call with context and dispatcher's default. That ensures, I need to probably import something, right? And this one as well, yes. Okay, this ensures that the execution of this method will be moved to a different thread. And as you remember, we can do this because this is a suspended function, which will be called in some coroutine context. And we change the execution of this coroutine to basically have it dispatched to a different thread. This dispatcher's default maintains a certain pool of threads, and the body of this function will be executed in a different thread than the UI thread. And this will be the same for all the methods. And what we implement here is exactly the same as well. So first of all, we of course need to take hold of our mutex, or the log object, however you call it. Then we need to ensure that our native synthesizer exists, right? Because we then need to call the native function. And we want to do it like this because this native wavetable synthesizer should only be the bridge between the Kotlin and the C++ code. So we only want to move the execution out, and we don't want to implement any additional logic because that's sufficient to maintain the information about the native object. So now let me quickly do the same with all the remaining methods. Okay, what you can see here is that I marked this return with this label, which means that by this return, we mean the return from this context. And this is actually, I don't know, is it required? Yes, it is required because we are inside the suspended function, so we need to indicate to which point we actually want to return. Okay, as you can see at the end here, I needed to retrieve the ordinal of this wavetable enum instance. So there may be a question from your side that maybe this mutex is not necessary because after all, we have this on resume and on pause. So what I found out was that at startup of the app, there was quite a bit of chaos. And it happened actually that the methods of these functions were called on the null synthesizer handle. And there are many ways you can deal with this. That's the way I decided to deal with this. Well, if you have a better idea, then let us know in the comments below. And as usual, all the source code is available on my GitHub, and you'll find link in the description. So now that we have the Kotlin part ready, we may proceed to actually adding C++ to our code. And the easiest way that I found how to do it is that we go here and we click Add C++ to module. And we choose that we want to create actually the CMakeLists.txt file. We don't want to point to an existing one, and we click OK. And what you can see is that actually, you'll see that in a second. Android Studio did a beautiful job here, creating the CPP folder. And what we have here is we have the folder with includes, which contains the headers of the NDK. We don't need to go as deep here, but it's good that we have this folder. And then we have the CMakeLists.txt file, which is used for compiling our code. And here you can see, as always, set which version of CMake we use, then the name of the project, and then the name of the library that we create. It must be shared, and the single source file that we have for now. And then what we need is we also link here against the logging library of Android. So first we find this library, and we assigned it to this variable, and then we link our library against this library. And this is, thanks to this, we can use logging to the logcat inside our C++ code. That's pretty awesome. So what I like to always do at this point is actually I'd like to sync, and let's see if we can build our module. All right, our project built, that's great. So we can stop the app and we may now proceed to implementing our native code. Here we have a handy instruction what to do actually, but let's remove this. And first, let's start by including the JNI header. And the JNI header contains everything that we need to interact with Java, or in this case Kotlin, thanks to their interoperability. Then we'll also need the memory header, and we also need a log header, but that's in a second, because that's the one that we'll have from our side. Sorry. So I like to use this square brackets or this angled brackets when I use the headers from the standard library, and the single quotes, the double quotes when I include my own headers. And then what we need here is we need to include also our wavetable synthesizer. And let's also comment this because we don't have the source file yet. And now we need to do an interesting thing. We need to write here extern C. And what it does is that this code will have so-called C linkage specification. And this allows us to write inside here C++ code that will be later compiled in a way that is compatible with C, and we need it for the calls of the JNI. Okay, now that we are here, we may proceed with creating our methods. So here we need to put the definitions of our external functions. And as you can see, they are missing here. But if I hover over it and I click create JNI function for create, we get this nice template that we can use. So we don't need to repeat this extern C because we just decided to use these curly braces. And what we have here is we have the declaration that this function is exported. Then we have the return type, and then the way how this function should be called. And then you have this nice name that informs the Java virtual machine that this will be actually the function that should be called upon the call to create. And as you can see, it's not read anymore. All right, so let's implement it. But first, also I wanted to show you that here we get a pointer to the JNI environment, which contains quite a few useful methods. And then here we have the access actually to the J object. So actually we have access to this object that called this function. That's really awesome. However, we don't need it right here. All right, so what we need here is we want to create our wavetable synthesizer. So we have here also synthesizer, right? And in std make unique, and we have wavetable synthesizer, wavetable synthesizer. So this is a class in a namespace that both don't exist yet, but we need to start somewhere. So now we check if our synthesizer got created, and now we can log, and this is another macro that we'll define in a minute. We'll call failed to create the synthesizer. So what we can do is we can log this in the logcat, and then we want to reset the smart pointer. And finally, what did we do? We return this memory address, this JLong, this long value, which will be then held by the synthesizer handle. So for this, we need to reinterpret cast to JLong, and must call synthesizer release. So the synthesizer release releases the ownership of this synthesizer pointer. And you may wonder, why do we use a unique pointer when we return this object immediately? Well, we do this because if somewhere here there was an exception thrown, then we would have a memory leak. So even here, although we don't need to call delete, we don't need to remember to call delete, we still use a smart pointer to be exception safe. Okay, and we may proceed and implement the next function, which is delete. And let's once again use this, not to make any mistakes. Perfect. And what we'll do here is that we need to, and this will be common for all the remaining functions, so we need to first retrieve a reference to our synthesizer using this synthesizer handle. So this is not nice casing, I prefer this one. And what we'll do is we want to retrieve the pointer to our synthesizer C++ object this time. So we do the reinterpret cast in the other direction. So we do reinterpret cast to a pointer of this type, right? And we'll do this on the synthesizer handle. And now, if it succeeded, we actually have access to our synthesizer. So we may write if not synthesizer, so if it didn't succeed, then we may write that we attempted to destroy an uninitialized synthesizer. And we return because there's nothing more we can do. But if we obtain a valid pointer to our synthesizer, we need to delete it to free the underlying memory. Okay, and now what happens is, again, we have like a nice template of calling a certain function. So let's say calling external function, then retrieving this synthesizer, and if the retrieval succeeded, then we call the corresponding function of the native C++ class, and if it didn't succeed, then we again log the failure. So let me use the automatic generation here. And what is nice is that I can simply click here and it navigates me to the desired function. Okay, let's put this here and let's remove this. All right, and let me copy this code. Okay, we have it here. And now have if the synthesizer is a valid pointer, then we simply call synthesizer play, because that's the function that we want to define. But if it isn't, then we log the failure. All right, and actually we can, we need a semicolon here, of course, and we actually can copy this multiple times. So again, here, and if the synthesizer is even called stop, and the same here, and here, and here, and here. Okay, and this is playing, right? So if then we return is playing, but if we don't have a synthesizer, then it definitely is not playing, so we simply return false. Then we have these nice parameters here, synthesizer handle, frequency in hertz. And again, we call here set frequency and we pass in the frequency in hertz. And then we have synthesizer handle in dB, set volume. All right, and here we will need this enum that I talked about. So let's write it like this. Call it native wavetable, and we'll have again this namespace. All right, something like this. And we pass it here. And also here, I think it's also important to cast these types to regular floats. All right. So this is everything that we need. In the source file, we can now comment these two lines. And now we proceed to create this WavetableSynthesizer C++ class. For this, we'll create a new folder. And here we'll create a new header file. We'll remove this dummy implementation. And we can put here pragma once means that it will be included only once. Then we have our namespace. And here we have our enum class wavetable. And just to be on the safe side, I want to mimic exactly the order that I have here. So I have sine, triangle, square, and saw. Perfect. And now already this should work, but maybe it still doesn't recognize that it's it should include. Yeah, it doesn't have this on its include path, so we need to modify our CMakeLists.txt file, but that will be in a second. So here we have class WavetableSynthesizer. Perfect. And we need to have our public interface, which will be again play stop is playing. As you can see, it's quite a bit of a boilerplate. Therefore, all the tools that generate it automatically are always welcome. And because this video would get too long, we'll again have a dummy implementation here that will only log that its methods were called. So now we can create our CPP file. Perfect. And we can include our WavetableSynthesizer header. And we also include again the logging header. And here we will have only logging that the member function of this class were called, but and we also maintain the coherence with the is playing state, but nothing more because the rest will be part of another episode. going to put it in our namespace. And now we have here. Let me open this. Oh no. Oh boy. Nope, no. Okay, and did it get modified here? No, unfortunately not. Okay, so let me hide this, and here we want to have our WavetableSynthesizer perfectly, so let me just copy this and paste this. Like this. Okay, and this is very simple, it's just log is playing called, and that's it. And here we can also have is playing set to true, and here we'll have stop called, and is playing will be false. Yeah, of course, this should be play. Okay, now return is playing. And now we actually want to log which arguments were used. So we'll get sec frequency called with have a specific argument, and we'll do nothing more because we don't have any other functionality. And now, okay, and I'm of course missing here volume in dB, the argument here as well. Okay, and the last member function, oof. And we again need to cast it to an int. All right. And that's all we needed. And now the last thing that we need from our source code is that we want to have here this log h header. Log. Okay, perfect. Again, we need to enter private var once. And here we include NDK specific header android.log /logh. And we want to have this code available only in the debug. So we write if not defined ndebug, which is very convoluted way to write that if we are in a debug. So if we are in the debug, we want to define our logd macro as a variadic macro. So we want to have multiple arguments. And let me maybe close this. And here we write this very long function, Android log print, Android log priority, Android log debug. I always forget how it goes, so I like these helper functions. Then we give it some label, and then we give it the arguments. Perfect. And in the opposite case, so when we are in the release mode, then we simply want to ignore anything. So this will be simply an empty macro. Okay, and what we now need to do is we need to update our CMakeLists because we have new files. So one thing that we need is that we need this WavetableSynthesizer CPP. I really like these auto-completion. And then what we need to do as well is we need to include directories. I will specify here include. And what it does is that it adds this folder to the path with the include. So now these headers will be properly imported. And that's actually all we need from here. So the last thing that we need to do is we need to go to our build.gradle file for our app. And as you can see here appeared an external native build. And so we have no CPP flags, but we can add, for example, that we want to use C++20. Oh, what happened? So we may write here cd equals to C++2a. And what we can also see is this, also in this Android section, but not the default configuration, but here we have the path to the CMakeLists.txt file and the version of CMake that we should use. And the last thing that we need to do is we need to wire this in our MainActivity.kt, but first maybe let me sync my Gradle files and then compile. So actually we have missing semicolon here. There will be a few things that may be wrong. Okay, I guess here should be a pointer type, right? And of course it's missing everywhere because we're not calling the constructor, we're merely casting to a pointer type. Okay, perfect. Let's try to build again. Okay, it actually succeeded, perfect. So the last thing, as I said, is we need to go to our... Nope. We need to go to our main activity, exactly. And here, as you can see, we have our logging wavetable synthesizer, so we'll change it to a native wavetable synthesizer, exactly. And what we'll do here is that we add the synthesizer as an observer of the lifecycle. And this single line will ensure that on resume and on pause will be called the same way as they are called in MainActivity.kt. And in this way, the native wavetable synthesizer will know when to destroy itself and when to create itself. And for this, we also want to remove this observer when this activity is destroyed. And everything else remains as it was. Okay, and now let's compile this and keep our fingers crossed that appropriate messages will appear in the logcat. Okay, awesome. As you can see, our wavetable synthesizer works because it already was called a few times. That's what I meant with this chaos at the beginning. So we need to be extra careful. And as you can see, it's not the logging wavetable synthesizer, but it's the wavetable synthesizer. It's actually the native wavetable synthesizer. So let's clear this and let's bring our app to the foreground and let's now test it. So we click play. And as you can see, we have isPlaying called and play called, and that is to determine the label of this button. So that's why it's called a few times. And now let's change the frequency. Exactly, we get the right argument in hertz, that's perfect. Now we change the volume. Perfect, we also got the volume change, and now let's change the wavetable. Exactly, so it's argument number 3, because we don't have any toString function that would interpret the names of these values. So actually this 0 is not interpreted, that's interesting. But other than this, like, our synthesizer works and logs. And now we can bring all of our audio processing into the C++ code. But before we do this, we need to connect to the Android audio driver. But this is how to connect from Kotlin to the C++ code using the Java native interface. In summary, in this part of the Android Wavetable Synthesizer tutorial, we have learned how to call C++ code from Kotlin on Android. Specifically, we learned what are external functions in Kotlin, how to use Java native interface with Kotlin, how to log to logcat from C++ code, how to compile native libraries for Android using CMake and Gradle, and how to handle the construction and destruction of native objects from managed code. In the next part of the tutorial, we will remove this dummy implementation and finally hear something. But first, we need to write some code to connect to Android's audio driver, which will be the topic of the next part. If you don't want to miss it, then subscribe and turn on notifications. And if you want to know what bits of knowledge are needed for audio programming, download my free audio plugin developer checklist under thewolfsound.com/checklist. Thanks for watching and see you in the next one. Take care.